Welcome friends, Igor is here, and in this video we will discover how changing a matrix affects its eigenvalues. In this lesson we will show that scaling a matrix scales its eigenvalues, raising a matrix to a power raises its eigenvalues to this same power, taking the inverse of an invertible matrix inverts its eigenvalues, and taking the transpose of a matrix does not change the eigenvalues. Let's get started. First, let's prove that scaling a matrix scales its eigenvalues. Let's assume that A is a square matrix and lambda its eigenvalue. Then there is a non-zero vector x such that Ax equals lambda x. I will show that this x is also an eigenvector of the scalar multiple of the matrix. Let's look at the matrix vector product. We will use the properties of matrix operation to factor the scalar multiple alpha, and our assumption says that Ax is lambda x. Now, using properties of vector operations, we can rewrite this as a scalar multiple of the vector x by the scalar alpha lambda. But this computation shows that x is an eigenvector of the matrix alpha A, which corresponds to the eigenvalue alpha lambda. In particular, this proof shows that while scaling a matrix scales its eigenvalues, the eigenvectors remain the same. Next, let's prove that raising a matrix to a non-negative integral power also raises its eigenvalues to the same power. Let's assume that A is a square matrix and lambda is its eigenvalue. Then there exists a non-zero vector x such that Ax equals lambda x. If s is equal to 0, then let's look what happens when we multiply the vector x by the matrix A raised to the power s. So this is a matrix A raised to the power 0. How do we interpret this matrix? Let's try to draw some analogy with numbers. A number raised to power 0 is defined to be equal to 1. So what is the analog of number 1 for matrices? This is the identity matrix. Therefore, let's define the zeroth power of the matrix A as the identity matrix. But multiplying any vector by the identity matrix does not change the vector. Also, the vector is equal to its scalar multiple by 1, and the scalar 1 can be represented as lambda raised to power 0, which in this case is lambda raised to power s. If s is at least 1, we are going to argue by induction on s. We will chip out one copy of the matrix A that stands next to x, and we use our assumption that x is an eigenvector for the matrix A with the eigenvalue lambda. Then we use the properties of matrix multiplication to move this scalar in front of the matrix vector product. And now we continue this pattern. We chip out another copy of matrix A that results in another copy of lambda, and so on. How many copies of the matrix A we have in total? We have s copies of the matrix A. Each such matrix contributes a factor of lambda. Therefore, we end up with this expression. But now you see that these computations show that x is an eigenvector of the matrix A raised to the power s regardless of the value of s, and the corresponding eigenvalue is lambda raised to the power s. Observe, while the eigenvalues changed, the eigenvectors remain the same. We can use this previous observation to prove now that when you apply a polynomial to a matrix, you also apply this same polynomial to its eigenvalues. We have not yet formally discussed what it means to apply a polynomial to a matrix, but it will become clear in the process of this proof. So we have a square matrix A and its eigenvalue lambda. This means there is a non-zero vector x such that Ax equals lambda x. Also, let's represent the polynomial q of x in the variable x as a polynomial of degree, let's say, m. Now, do you see what it means to apply a polynomial to a matrix? We can raise matrices to non-negative integral powers. Then we can take scalar multiples of these matrices, and finally we can add up the resulting matrices. This computation will yield a matrix of the same size as the original square matrix A. So we use the distributive property of matrix multiplication. Then we factor out the scalar multiples. And now we use the last theorem. Next, we use the properties of vector operations and we factor out vector x. Now all that remains to observe is that this whole thing in the parentheses is simply polynomial q evaluated at lambda. If you look at the beginning and the end of this computation, you see that it tells you that x is an eigenvector for the matrix Q of A, and the corresponding eigenvalue is Q of lambda. Once again, observe that eigenvectors did not change. Next, if we have an invertible matrix, then the eigenvalues of the inverse of the matrix are inverses of the eigenvalues of the original matrix. Let's observe that to be invertible is the same as to be non-singular, and in the previous video we proved that non-singular matrices have only non-zero eigenvalues. Therefore, multiplicative inverses of all eigenvalues do indeed exist. Let's take an eigenvector x for the matrix A corresponding to the given eigenvalue lambda, and we will compute the matrix vector product A inverse multiplied by the vector x. I will replace the vector x with its scalar multiple by the scalar 1, and I'm going to represent the scalar 1 as 1 over lambda times lambda. Then, using properties of matrix operations, I'm going to move 1 over lambda in front of the expression. But x is an eigenvector, so lambda x is the same as ax. Next, let's use the associative property of matrix multiplication. And A inverse times A is the identity matrix. But identity matrix multiplied by the vector x is just the vector x. And now, if you look at the beginning and the end of this computation, it tells you that x is an eigenvector for the matrix A inverse, and the corresponding eigenvalue is 1 over lambda. Observe once again, the eigenvectors remain the same. Finally, let's prove that taking the transpose of the matrix does not change the eigenvalues. For this, let's look at the characteristic polynomial of the matrix A. It is defined as the determinant of the matrix A minus the scalar multiple of the identity matrix by the variable x. In one of the previous videos, we have proved that taking the transpose of the matrix does not change the determinant. Next, we are going to use the property of the transposes that transpose distributes over the addition of matrices. Next, we are going to use another property of transpose that scalar multiple gets factored out from the transpose. But now, let's observe that the transpose of the identity matrix is still the identity matrix. It is a symmetric matrix. But now you should recognize that this determinant is precisely the characteristic polynomial of the matrix A transpose. This proves that the matrix A and A transpose have the same characteristic polynomial, and therefore they have the same eigenvalues because eigenvalues are roots of the characteristic polynomial. This result is in contrast with all the previous results we proved in this video. In the previous results, eigenvalues have changed, but eigenvectors remained the same. But notice that in this proof we did not use eigenvectors. This is because when you take the transpose of the matrix, eigenvalues remain the same, but the eigenvectors may actually change. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will define the notion of similar matrices and discover some of its properties. I will see you later.